In programming, a developer can create a variable of a specific size. Imagine a variable containing a username with a memory allowance of 10 characters. Technically speaking, there is nothing stopping you from entering a username with more than 10 characters. But if the developer hasn't implemented code to check if the size limit has been exceeded, what is happening on your computer? Is data that exceeds the variable ignored? Unfortunately not, and this can be abused by hackers. Welcome to stack buffer overflows. On a computer, every single running process has its own separate memory space. The layout of that memory is called the stack heap memory. The stack is the space used for function calls, local variables, and managing the program execution flow. On the other hand, the heap's goal is for dynamically allocating memory for variables with dynamic size or lifetime, such as those whose size cannot be determined at compile time. In simple terms, the stack is where a process keeps track of what to do next. The heap is where a process keeps track of every dynamic variable. We will see later what a dynamic variable and what the heap is. For now, we will see the stack in more details. If we figuratively zoom into the stack, it should look like this. The ESP, which is short for Extended Stack Pointer, keeps track of which stack frame we are currently on. Each function has its own stack frame, and every stack frame is composed of a buffer space, an EBP, and an EIP. A buffer space will store the contents of temporary data. In our example, this will be the content of the username variable. The EBP, which is short for Extended Base Pointer, is a reference point used by the computer to keep track of important information inside a function. It's like a label that shows where different things are stored. The EIP, which is short for Extended Instruction Pointer, keeps track of the memory address of the next instruction to be executed by the CPU. If we are able to enter a username higher than its allocated size, then we can overflow the buffer space and enter the EBP. If we continue to enter data until we reach the EIP, then we can simply overwrite the memory address of the next instruction to be executed by the CPU. In other words, it is possible to change the execution flow of a program, and therefore order it to do something that we have decided it should do. In order to practice, we need to set up our environment. If you are watching this from a Windows machine, then we'll just need to have a Kali Linux virtual machine, which you should already have by now. If you are watching this video from another operating system, then please create a Windows virtual machine. Microsoft allows you to download Windows 10 from the Windows Evaluation Center. Then let's download and install Vuln Server from the gray corner on your Windows machine. Since this is an intentionally vulnerable server, it is more than likely that Windows Defender will categorize Vuln Server as dangerous. To counter this, you must deactivate Windows Defender. To do this, you must open the Windows Defender settings and deactivate protection against threats and viruses. We also need a software called Immunity Debugger. This is important because it allows us to see the insides of our program and see in real time what we are doing. Once everything is installed, start Vuln Server and then Immunity Debugger as administrator. Now we need to set immunity to debug our Vuln Server program. So we need to select File, Attach, and select Vuln Server, and then click Attach. We are looking into the memory of Vuln Server, but as you can see, it is written paused. So we are currently debugging Vuln Server, but as you can see in the bottom right corner, there is the mention of paused, which means that we are not currently debugging Vuln Server in real time. To counter this, we need to start the debugging process, thanks to this icon, which is Run Program. Once you click on it, the debugging is actually running. The interface definitely looks daunting, but do not worry. I'll explain what to look for as we go. Let's first connect to our Vuln Server machine. I know that my Windows machine IP address is 192.168.122 and 8. If you do not know, just check on your Windows machine with the ipconfig command. The port for Vuln Server is 9999. If we press Help, we have a list of all the valid commands. All those commands can contain a value, thus we need to test each of them in order to find out if one of them is vulnerable. Finding out if a variable inside a program is vulnerable is easy. You just need a very simple script that will send data in an increasing manner until the program breaks. If it breaks, it simply means that we have overwritten the EIP, and the process has junk inside its EIP that it does not know what to do with. This part is called spiking. Let's try to spike Vuln Server and choose srun as an example of a non-vulnerable variable. Our script is the following. We simply specify to write srun every time we connect and append a variable to it. We are going to use a tool called generic sendTCP for the spiking, and the syntax is as follows. Let's try it out. We can notice that we are sending even larger and larger variables on our Kali machine. Unfortunately, the program does not seem to crash. It even says running at the bottom right corner, which most likely means that srun is not vulnerable. Let's stop our fuzzing with Ctrl+C and try the next variable on the list, which is trun. We just need to modify our spike script to fuzz trun instead of srun and launch a new test. Now this is more interesting. Vuln Server crashed. It does not do anything anymore. Immunity Debugger is paused, and we even have a nice debugging message at the very bottom. Access violation when executing 41414141. Let's look at the register pane. On the very first line, here is what we are sending to Vuln Server. We are sending the command trun with many capital A characters, just like in the image earlier when we looked at the specifics of the stack. If you look closely, we can also notice that the contents of the EBP is a bunch of 4 ones and the content of EIP is the same. Well, the ASCII table, which is the table containing all the numerical values associated with each keyboard characters, tell us that 41 is the hexadecimal number for a capital A. In other words, Immunity Debugger is telling us that we have overwritten the EBP and the EIP with capital A's. Spiking is a success. Before we continue, please make sure that Immunity Debugger is restarted. We can do it by pressing debug, restart, and press running again. Now we need to fuzz. It's a little bit like spiking, but we want to send 100 A's at a time to roughly find how many characters are needed to break the program. It will be important for the pattern creation. The script is as follows. Feel free to pause the video to copy it, and then run the script. We stopped the script right when the program crashed, and the program crashed at roughly 3000 bytes. Now we need to find out exactly how many characters are needed to enter the EIP space. Remember, this is the thing we want to control. We want to write specific instructions inside this space. In your Kali VM, there is a tool called Pattern Create, which is available at User Share Metasploit Framework, Tools, Exploit, pattern-create.rb, and let's create a pattern of 3000 bytes. No need to generate more than this. As you can see, the pattern is making it impossible to confuse a pair of characters with another. Let's add it to our script. This is the Python script that will host our pattern. Let's restart Immunity Debugger once again and start our script. Now, in Immunity Debugger, the EIP contains 386F4337. Now, in Immunity Debugger, the EIP contains 386F4337. We had Pattern Create. Let's now use another tool, which is Pattern Offset, and ask it how many characters are needed to reach 386F4337, and the answer is 2003. So, at 2003 bytes, we can control the EIP. If we did find the right offset, we could modify our script and write 2003 A's followed with 4 B's. The EBP should be filled with 41s, while the EIP should be filled with 42s. The next thing we need is to find if there are any bad characters. What I mean by that is that our reverse shell is going to be written in shellcode, and some characters from that shellcode might be misinterpreted. To counter that, we need to throw every single shellcode character to the program and see if it interprets them all in a correct manner. Let's grab all the bad characters from Sitopia and create a script to test all bad characters against Boon server. How do we know what characters are well interpreted? Well, in Immunity Debugger, we can see every single possible symbol by expanding the address pane. Right-clicking ESP and selecting Following Dump. All the characters are there, and they all have the hexadecimal equivalent written. It starts with 1, 2, 3, 4, 5, 6, and it goes on and on. If there was a bad character, let's say at 22, instead of having 21, 22, and 23, we will have something such as 21, B0, 23. Basically, the numbers will not follow the incremental order. Thankfully for us, there does not seem to be any bad characters beside what is called the null byte, which is always a bad character. We are almost done. We need to find the right module now, which means that we need to find something such as a DLL inside our Voon server program that does not contain any kind of memory protection in place. In order to find the right module, we can install Mona.py inside Immunity Debugger. Mona.py can be downloaded on the GitHub page, and it should be placed inside C Program Files Immunity Inc. Immunity Debugger py commands. Now, in Immunity, we need to enter at the very bottom the command Mona modules. We're in luck because essfunc.dll has 0 memory protection in place. We are going to use this one. Now let's write monafind-s \xff xe4 -m essfunc.dll. Just so you know, xff and xc4 is a jump instruction, meaning that we are searching for a return address. And we got one, 625011AF. Let's modify our script and specify our return address after 2003 bytes. If you are wondering the reason why our return address is written backwards, it is because this is how the x86 CPU architecture that you are most likely using right now works. We can create a breakpoint by searching for the return address and then pressing F2. Then let's run our script again to confirm that we are providing the right return address with the right module in the EIP. And we are indeed controlling the EIP. It says EIP 625011AF essfunc. Now let's generate a reverse shellcode with MSF Venom, copy the payload, and paste it inside our script. So this is the MSF Venom payload we have to create. We have to create a payload for a Windows machine, a reverse shell, and TCP for the local host, which is our IP address on a port that we specified. We should also listen to this port, otherwise we don't receive any kind of connection, of course. And we also have to specify the architecture, so it's x86, and we have to exclude the null byte bad character that we specified earlier, so a \x00. Then we have to copy this whole payload and add it to our script. Here is our final script. We do not need immunity anymore. Let's restart Vuln server, listen on the port we specified in MSF Venom, and launch this script. For the record, \x90 32 times is simply some padding we add just to make sure that we are not overriding anything. It's a security measure just to be sure that our shellcode is going to be properly executed. Now, if we start this script, we should instantly receive a shell on the Windows machine from our Kali VM in the pane right below where we are actively listening on port 1234.